viewers, myself Dr. T. Anodha, presenting a new video to you. The title is Molecular Structure Determination from the Spectral Data, mainly NMR data. This video will be very useful for examination purpose and other examinations as well. So please listen carefully. For simplicity and clarity of the subject, the whole video has been divided into several subtopics listed over here. Introduction part. Analysis of spectral data is learned through exhaustive practice. Let us embark upon this problem, taking few simple examples. Among the noteworthy features of the spectra are the following. First, number of NMR signals, most important feature. Second, relative area under the peaks. Third, splitting of peaks, that is peak multiplicity. Fourth, relative intensity of the lines of the multiplet. Fifth, coupling constant, J values. Sixth, effects of adding D2, heavy water. Seventh, effect of changing temperature. Eighth, effect of using higher magnetic field so as to spread the spectrum. Ninth, effect of addition of shift reagents. These days less commonly used. Earlier they were very important. 10th, additionally, the relaxation time is also an important NMR parameter. So the whole video will be discussed using some of these points. Some of the other points will be covered in later videos. Step 1. First, the number of NMR signals and their chemical shift positions, that is delta values, on the spectral chart should be noted. The number of NMR absorption signals reveal the types of chemically distinguishable or non-equivalent groups of hydrogens in the molecule being studied. While their delta values indicate the type of chemical environment in which the hydrogens are located. Step 2. After noting the signal numbers and their positions, we proceed to electronic integrator readings of each signal. It should be carefully measured. These are found to be roughly in the ratio of the number of absorbing nuclei, that is hydrogens, in each chemically non-equivalent group. Step 3. Chemical shift values for such type of H. The range given below are porous, not strictly impermeable. However, these are indicative and thus practically very useful. Table 1 lists the range of chemical shift relative to TMS. For TMS, the value is 0.0 delta ppm in CdCl3 solvent. From delta 14 to 12, we observe the carboxylic acid proton and phenolic protons. From 12 to 10, we observe enolic protons. From 10.5 to 9.5, aldehydic protons. From 9 to 6, aromatic hydrogens. From 6 to 4, alkenic hydrogens. From 5 to 3, hydrogens directly linked to carbon, which is carrying a oxygen directly linked to it. Range 3 to 2, acetylenic hydrogens. Range 2.6 to 2.1, ketonic hydrogens. Range 1.9 to 0, saturated CH, both cyclic and acyclic. Range 0 to 2, alkyl metal types, and beyond we have alkyl hydrides. As can be seen, the chemical shift values provide very useful clue regarding the chemical environment of the hydrogens. And chemical shift values depend upon several factors We will be discussing these factors in later videos. Step 3 continued. The concept of shielding and de-shielding. The following sketch is illustrative of the mechanism of origin of chemical shift. Negative sigma I B0. In this, sigma I refers to the screening constant of the ith nucleus and B0 refers to the applied magnetic field. Applied magnetic field increases from left to right and absorbing nuclei are surrounded by electronic cloud. Local field is created. This local field B local is equal to minus sigma I B0. Therefore, the field effective at the nucleus is given by B0 bracket में within bracket 1 minus sigma I equal to field at the nucleus. Here, the direction, shielding and de-shielding, they are also shown. Shielding increases from left to right. De-shielding increases from right to left. Again, step 3 continued. When the external magnetic field is switched on, a small magnitude of diamagnetic field is induced due to the bonding and non-bonding electrons around the absorbing nucleus. This field called B local serves to modify the applied field B0 so that the field effective at the nucleus may not be the same as B0. This shift value is designated as minus sigma I B0, which is directly proportional to field B0 and is called chemical shift, a field dependent parameter. In this, sigma I is known as the shielding or screening constant for the ith nucleus. It is a dimensionless parameter of very small magnitude measured in parts per million, and it is related to the diamagnetic susceptibility of the parameter. Truly speaking, minus sigma I B0 is defined as the chemical shift for the ith nucleus. This field-dependent parameter is converted to field-independent dimensionless parameter, delta scale, through the following equation. The equation for the calculation of chemical shift in universal scale, that is delta ppm, is shift in frequency, that is delta nu, relative to the frequency for TMS, divided by operating frequency, whole multiplied by 10 to the power 6. Why do we use this multiplier is explained later. The shift is measured in Hertz. When it is measured in magnetic field unit, Tesla or Gauss, the denominator is also taken in the field unit, that is B0. The multiplier factor is used to convert very small values which are difficult to memorize to such values which can be easily memorized. And this ppm, which means multiplication by 10 to the power minus 6, corrects the addition of 10 to the power 6 multiplier. This is very important to remember. Why do we use 10 to the power 6 and why do you use ppm? Both cancel each other. Illustration of chemical shift. Frequency increases from right to left. Shift is measured relative to the reference signal, TMS signal. The delta scale usually runs between 0 to 8. And for other values beyond 8, half field signals are indicated. The left side is downfield side, the right side is upfield side, and chemical shift is in the universal scale delta, which is dimensionless. The order of delta value is in relation to the type of hydrogen environment. RCOOH followed by RAROH followed by phenol followed by aldehyde followed by alkene followed by alkene followed by OCH followed by alkyne followed by double bond OCH followed by saturated CH, then TMS, and beyond that alkyl metal alkyls. Metal hydrides and metal alkyls, for example, absorb between delta 1 to 20 negative value. It is beyond the signal for TMS. The higher electron density means more shielding, and low electron density means less shielding or de-shielding. Some representative delta values are for benzene it is 7.3, for chloroform it is 7.27, for methylene chloride it is 5.23, for CH3X where X is halogen 3.8 to 3.1, respectively for fluorine, chlorine, bromine, and iodine. For cyclohexane, the value is 1.44. Tetramethyl methane, the value is 0.9. Methyl attached to benzene ring is 2.3. And methyl dimethyl sulfoxide is 2.5. So some representative data you should memorize. It is not difficult to memorize. They give you an idea about the position of peak and type of H. You need not remember very large number of data, but some representative data you should remember. Example 1. How do we use the data? Two compounds of the same molecular formula, C6H12, can be distinguished on the basis of such data. Cyclohexane, for example, data is 1.44 ppm. Tetramethylethylene, same molecular formula, data is 1.82 ppm. So the data, the chemical shift value is very much indicative and informative. Example 2, we have considered an example, molecular formula C2H2Br2. Three structures are possible. 1,1-dibromoethane with ethene. One signal on split. 6,1,2-dibromo and trans 1,2-dibromo. Both have one signal, but the positions of delta values are different. Sometimes NMR alone cannot solve the problem, and we require additional data from IR, from mass, from other spectral features. Electronegativity has profound effects on delta values. Some data are given here. In CH3X, where X is fluorine, chlorine, bromine, iodine, the data are 4.13, 2.84, 2.45, and 1.98. That's a drastic difference. So electronegativity plays very important role. Another example is 1,3-dichlorobenzene, 4-nitrofluorobenzene, diethyl ketone, ethanyl, 1,1,1-trifluoroethane, and butene 2,3-dione. 1,3-dichlorobenzene shows three signals in the range delta 8 to delta 7 ppm. The hydrogen at C2 is a singlet. Hydrogen at C4 and C6, same chemical environment, appear as a doublet. Hydrogen at C5 appears as a triplet. 1,4 isomer of fluoronitrobenzene presents a very special case. In this case, we have two sets of chemically mutually equivalent hydrogens, and these chemically equivalent hydrogens are not magnetically equivalent. Therefore, a very special case. The signal of H is also split by fluorine. Complex spectrum results. In case of diethyl ketone, we observe two signals, one for methyl, another for methylene, both split. Methyl signal is a triplet. Methylene signal is a quartet. In acetaldehyde, we observe two signals, a quartet for the aldehydic proton doublet for the methyl. In CH3CF3, one quartet splitting is caused by three fluorines. In case of 2,3-diketobutane is very complex because it shows keto in alpha-atomerism. So a number of signals appear. Most compounds exist in equilibrium. Another example, we have taken C2H4O, the molecular formula. It shows a quartet and a doublet. We have to decide the structure. So the structure is ethaneal or acetaldehyde. The value lies between delta 9.5 and 10.5. Doublet for methyl, quartet for aldehyde proton. Molecular formula C4H9Br. If it shows one signal, it is tertiary butyl bromide. If it shows three signals, it is isobutyl bromide. If it shows four signals, it is N-butyl bromide. Molecular formula C4H10O. If it shows two split signals, triplet quartet, then definitely it is diethyl ketone. Molecular formula C4H8O shows two signals, but no OH, no C double bond O. It means it is tetrahydrofuran. So what I mean to say, first you note down the number of signals, then their positions, then splittings, whether doublet, triplet, quartet, quintet, etc., or singlet, unsplit. So all these features, all these information help you analyze the spectrum and reach at the structure of the molecule.